Assalamualaikum. I'm ZULHELMY and I am the Chief Executive Officer for Dimensionless.
Hi, my name is SCHERILYRA and I'm the Chief Financial Officer.
Hi, my name is DAMIEYA. I am the Personal Assistant.
Hi, my name is NURFATIN AMANI as an intern.
I am HASSIFAH and I am the manager.
For reaction engineering part, our objective was to design an efficient reactor system that maximizes nitric oxide production while minimizing unwanted byproduct. We will cover the reaction kinetic, catalyst selection, reactor selection, reactor sizing, and optimal operating condition. Let's go. Nitric oxide is widely used in both medical and chemical industry. In medicine, it is essential for treating pulmonary hypertension and neonatal hypoxia as it helps dilate blood vessels and improve oxygenation. Industrially, nitric oxide is a key intermediate in osmotic process where it is converted into nitric acid, an important raw material for fertilizer and chemicals. The challenges in nitric oxide production lies in achieving high selectivity and efficiency while minimizing byproducts such as nitrogen dioxide and unreacted ammonia. This study focused on designing a high-performance reactor system to ensure sustainable and efficient nitric oxide production at an industrial scale. The production of nitric oxide occurs through the catalytic oxidation of ammonia following this reaction. 4NH3 plus 5O2 which produce 4NO plus 6H2O. However, a sad reaction occurs, forming unwanted nitrogen dioxide. The reaction follows third-order kinetics, where the rate depends on second-order ammonia concentration and first-order oxygen concentration. For this process, we selected a platinum-rhodium catalyst because it offers high selectivity, which ensures more nitric oxide production and fewer byproducts. It is also resistant to poisoning, which extends catalyst lifespan, then reducing the maintenance cost. Lastly, it can withstand a high temperature required for efficient nitric oxide formation. Without an efficient catalyst, unwanted side reaction will dominate, leading to lower nitric oxide yield and increased nitrogen dioxide formation.
Next, we move to reactor selection. We consider three reactor types for nitric oxide production. First one, CSTR, PFR, and PBR. And finally, we choose PBR as the best choice due to the efficient heat management for exothermic reaction, higher conversion rates than other reactors, and lastly, better catalyst utilization, making it cost-effective. Next, the reactor sizing. We use Levin spill plot to calculate the required reactor volume. The result shows that CSTR required 8.704 meter cube. PBR only needs 1.551 meter cube, which is smaller and more efficient and lower operational costs. The expansion factor, which is 0.1211, was also considered to account for the change in gas flow during the reactions. This will ensure our reactor design efficiently handle the process condition. So why the reactor sizing is so matters? It is so important to optimize reactor size, improve and cost efficiency. Smaller volume also need lower material costs and better heat management. And this sizing also matter because it will ensure high conversion of ammonia to nitric oxide. Through sensitivity analysis, we determine that the optimal condition for maximum nitric oxide yield are 900 degrees Celsius and 91.33 kilopascal. As shown in the graph, higher temperature improve ammonia conversion, but beyond 900 degrees Celsius, side reaction will increase. Lower pressure also favor nitric oxide formation as predicted by the Chatelain principle. In conclusion, we successfully designed a PBR reactor for nitric oxide production. Our study confirmed that using a platinum-rhodium catalyst at 900 degrees Celsius and 91.33 kilopascal will maximize the nitric oxide yield while minimizing the byproduct. Future improvement could include energy recovery strategies, process automation, and further catalyst optimization to enhance efficiency and sustainability.
Today, I'll present the absorption-based purification process for medical-grade nitric oxide. Given its critical role in healthcare, nitric oxide must be 99.9% pure, requiring effective removal of impurities like nitrogen dioxide, ammonia, and nitrous oxide. The purification occurs in three key stages. First, nitrogen dioxide removal. Potassium permanganate oxidizes nitrogen dioxide, forming stable byproducts and reducing its concentration to below 1 ppm. Second, ammonia removal. Zeolite absorbs ammonia molecules efficiently using the friendly isotherm, preventing toxicity. Third one, nitrous oxide removal. Zeolite is also used here, operating under the Langmuir isotherm to ensure complete nitrous oxide capture. This exhaustion-based method is energy efficient, scalable, and cost-effective, making it ideal for continuous nitric oxide purification.
Next, we will moving on to the adsorbent selection. This selection is based on the adsorption capacity, selectivity, regenerability, kinetics, compatibility, and cost. The selected adsorbent must effectively remove nitrogen dioxide NO2, ammonia NH3, and nitrous oxide N2O while ensuring a long-term operation. For the removal of NO2, potassium permanganate KMnO4 is used as the adsorbent. This is because it is a strong oxidizing agent, has high selectivity and capacity, and has a fast adsorption kinetics. Next, zeolite is used for the NH3 removal because of its microburr structure other than having superior selectivity. It is also a regenerable and cost-effective adsorbent. Zeolite is also used for N2O removal. This is because it can still operate under moderate pressure adsorption. It is also a sustainable and reusable adsorbent other than complying with industrial compatibility. Moving on to the selection of adsorption isotherm. This part is important since it determines how NO2, NH3, and N2O interact with KMnO4 and zeolites. Out of 3 isotherms learned, only 2 types is involved in this study. First, Langmuir isotherm for both NO2 and N2O adsorptions. Langmuir model fits these adsorptions due to monolayer behavior and strong adsorbent-adsorbate interactions. The second one is Freundlich isotherm for NH3 adsorption. This is due to multilayer adsorption on heterogeneous zeolite surfaces.
This is the design of our adsorption column and the details of the materials used and multi-stage process. The column must handle high gas flow, pressure changes, and chemical interactions. Hence, for the column body and support grid, we use stainless steel 316 for its corrosion and high pressure resistance. Ceramic beads act as an inert filler for uniform flow. Perforated stainless steel sheets contain the adsorbent, while a PTFE coating prevents NO2 corrosion. Since this is a multi-stage column, the top layer uses KMnO4 as absorbent to remove NO2, while the bottom layer with zeolites that target NH3 and N2O. These chosen materials and stage design ensure efficient and durable impurities removal even under demanding conditions. Now let's look onto our purification efficiency strategies. Our main goal is to achieve 99.99% purity, which signifies the medical grade checkmark. To achieve this high standard, we employ several key strategies. Firstly, adsorbent regeneration. This is crucial for maintaining and improving the lifespan and efficiency of the materials we use for purification. Think of it as keeping our purification tools in top condition. We utilize 2 primary adsorption techniques, pressure swing adsorption or PSA, which specifically targets and removes NH3 and N2O, and thermal swing adsorption TSA, which focuses on eliminating NO2. To maximize our efficiency, we combine these 2 methods into PSA-TSA hybrid. This approach ensures the removal of all impurities, optimize energy use, and guarantees a consistent supply of high purity nitric oxide, all while keeping the operational costs down. Complementing these methods is our multi-stage adsorption process. This involves using specific adsorbents for each byproduct, ensuring we remove the majority of impurities right from the start. In essence, our strategy for achieving 99.99% nitric oxide purity is a comprehensive approach that combines adsorbent regeneration, targeted absorption, and multi-stage processing. This ensures not only the highest purity but also efficiency and cost effectiveness.
Before discussing the parameters of the column, some assumptions need to be clarified. The system is assumed to be in a steady state operation, block flow behavior, having constant temperature and pressure. Pressure drop is negligible, considering MTZ is 20% of the column, and lastly, adsorption equilibrium follows isotherms. After calculations using the respective formulas, it is decided that a column with diameter of 1.49 meter, height of 0.6 meter, and MTC of 0.6 meter is to be used for our study.